recording.
Hi, everyone. This is our presentation for the final project in our big data class. My name is Henry Birch, and my partners are Guy Wood and Harrison Tognella. This presentation is going over part A, which is evaluating the reproducibility of deep learning. So the first question is how deep learning models suffer from reproducibility. So deep learning models face significant reproducibility challenges due to various factors. Seeding, while helpful, provides only partial control as randomness is introduced from multiple sources. These include loss function optimization, and GPU speedup. Also, identifying and quantifying the reproducibility of deep learning models is essential for advancing research and applications in the field. Despite the inherent challenges, understanding which deep learning models exhibit higher reproducibility is a crucial step toward addressing these issues. Now, here's the project overview of what we're presenting today. So first, we have the model architectures, which design and build. In the model architectures section, we designed and built a DNN, CNN, LSTM, and GRU models, and we used ReLU activation functions. And we also drew the architectures of each model. Next, we chose optimizers and loss functions. Then we ran the models. Each we ran 5 times with 100 epochs each. And during this, we calculated the CLRs and D-index for each run and visualized them. And we did this to identify which models had the best reproducibility. So once again, we ran each of them 5 times with 100 epochs. And for each model, we compared them to see which is most reproducible. And after doing this, we repeated this process 3 more times. One time, we applied PCA and TSNE before the models to see how this would change it. The next time, we actually just extended the models to more than 7 layers. Because before each model had roughly 3 to 4 layers, but now they have 7 to 10 layers, just to see if adding more complexity increased or decreased reproducibility. Next, similar to the PCA plus TSNE, we just added PCA without TSNE to see how this would also affect reproducibility. And the last step was to compare the results and learning behaviors of each model. Now, CLR. CLR is one of the tools we're using to measure the reproducibility of each model. The definition of a CLR is that it measures the ratio of a correct classification by a model after n runs, with each run consisting of 100 epochs. And the representation is that a CLR is the average classification ratios of n runs. So here's a scenario, which is our example for a DNN. Suppose a DNN undergoes n runs, and its accuracies are accuracy 1, accuracy 2, all the way through accuracy n. The correct learning reproducibility, or CLR, of this deep neural network is calculated as the sum of every accuracy divided by the total number of runs. So as you see, it's alpha 1 plus alpha 2 plus dot 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 alpha n, all divided by n. The usage here is that the CLR serves as a quantitative metric to assess the reproducibility of deep learning models. A higher CLR indicates greater consistency in the model's ability to correctly classify data across multiple runs. The application is that CLRs can be employed to compare the reproducibility of different models, helping researchers and practitioners select models with more stable and consistent performance. Now for the 3 data sets. We are running this for all the steps I described previously. We're doing all that on 3 total data sets. The first one is the MNIST. This is a standard data set for handwritten digit recognition and machine learning. It contains images of the digits 0 through 9, all handwritten, and the size is 6,000 by 28 by 28. Next is the EMODB data set, and this is a speech emotion recognition data set. It comprises of 535 short phrases, each with 7 emotional tones. And as you can tell, the size is 535 by 7. The last one is the KOLOD or COLOD dataset. This is actually a publicly available dataset for single cell RNA sequencing data. It consists of 704 samples, which are categorized into three classes, either embryonic stem cells, neural progenitor cells, and neural crest cells. And we classify these as either 0, 1, or 2. And this data set was the most complicated and most difficult to run on. It took the longest because it only has 704 entries. However, it has 10,686 columns or features, which may take a long time to train on. So the smaller the model and the simpler the model, the better, which is really interesting for our model complexity and reproducibility. Now, Guy will take away and explain each model we did.
So as Henry just mentioned, he was talking about how for each data set, we were looking at different types of data. So we had our normal data, then we had our data where we did PCA and TSNE, and then ran models on the embedded data. And then we used just the normal data and did deeper models. And then finally, we worked with just PCA data. Now for each of those types of data, we had to run 4 models, and we had to run a DNN, a CNN, an LSTM, and a GRU model. So here is just an example of one of our DNN models. Now DNN stands for Deep Neural Network. So you can see from the function on the left, this is just a snippet of the function that we made. And so you can see from this code here that we are inputting into the function our xtrain, ytrain, xtest, and ytest data. And our number of attempts equals 5. That just means that we're going to be running through this model 5 times, each time with 100 epochs. So you can see with this model that we're first going to flatten the data. And then next we have our first hidden layer with 200 neurons, then a layer with 100 neurons, 50 neurons, and then finally 10 neurons. And that's because there are 10 classes in the MNIST dataset. So we ran that, and then you can see on the right our results. So we outputted the correct learning reproducibility, or the CLR, which Henry previously mentioned. And then we talked about the standard deviation of accuracy, and then also the average d-index value. So we have in the graph here, this is a graph of the d-index value for all 5 runs. And you can see at the top the average d-index value across the 5 runs. So the next model that we did was a CNN, or a convolutionary neural network. And kind of the same thing as the last slide. You can see a little snippet of the code for how we made our CNN model. A little bit different than the deep neural network, but you can see all the code there for that model. So we have 2 convolutionary 2D layers, and then we did max pooling. We flattened the data. Then we had a dense layer with 128 neurons. Then we added some dropout to reduce overfitting. And then we finally, as our last layer, had a dense layer with 10 neurons, because that's the number of classes that our data set had. And then you can see on the right the results as well, where we have our correct learning reproducibility, which is our CLR, our standard deviation of accuracy, and finally our d-index value for each run and the average across the 5 runs. The next kind of model that we did was an LSTM, which stands for long short-term memory. And so with this model, again, you can see the code here. So once we ran this function, we were able to get the results again, like we did in the previous slides or with the previous models. And so after we ran this code on our xtrain, ytrain, xtest, and ytest data sets, we ran it 5 times, each time at 100 epochs, and we can calculate the correct learning reproducibility, the CLR, the standard deviation of accuracy, and the average d-index value for all 5 runs. And then we also plotted each d-index value for each run. And the final model that we did was a GRU model. And so you can see from the code, this model is not a super complicated model, but we have our first layer is a GRU layer, and then we go right into a dense layer with 128 neurons. Then we add a dropout to make the model more robust to overfitting. Then finally, we close off our model with a dense layer with 10 neurons because our data set has 10 classes. And then again, ran that model for 100 epochs and ran it 5 times. And then we can see our correct learning reproducibility, our standard deviation of accuracy, and our average d-index value. And then also we plotted each d-index value for each run. So all the snippets of the models that we just talked about were just from our models on the normal data from the MNIST data set. So we also had to run these models for other data sets and also for different types of data for each one. But this right here is just a table of the results that I just talked about in the previous slides. So this is just a table that combines all this so you can easily see it. Now, the point of this project is to determine which models are more reproducible. And we do that by looking at the CLR and the standard deviation of the accuracy values. Lower standard deviation generally indicates better reproducibility. Based on the provided table, the MNIST deep neural network has a standard deviation of 0.54 for CLR, suggesting moderate reproducibility. The CNN has very low standard deviation of 0.16 for CLR, indicating high reproducibility. The LSTM model has a standard deviation of 0.43 for CLR, suggesting moderate reproducibility. And then finally, the GRU model has a higher standard deviation of 0.88 for CLR, indicating lower reproducibility. Therefore, as we can see from these results, that the CNN is the model with the highest reproducibility among the 4 models. Now, one thing I want to add here is, so this is just the results from one of our data sets and for one of the data types. And so based on the whole project, what we had to do is we had to make 16 models per data set, and there were 3 data sets. So for example, what we just talked about right here and looking at these results, these are the 4 models that we made just for our normal MNIST data. And so we also had to compare this with the MNIST data using PCA plus TSNE. Then we also compared that to making our models even deeper to where they have at least 7 layers each. And then finally to the PCA data by itself. And we compared all of those results together and just did the steps that Henry and I just talked about, but did them over again 4 times for each data set. And then we also looked at the COLOD and the EMODB data sets as well.